As we transition into the public phase of the Breakthrough campaign, it's important to ask, why are we doing this? What is the campaign all about? It's about harnessing the fearlessness, the inventiveness, the curiosity of the Caltech community to create knowledge for the ages, but also to solve pressing problems that affect society today. It's our quadquicentennial, that is our 125th anniversary. So it's a natural time to look back at what's made Caltech successful, but it is also a wonderful time to look forward. How can we use what we've learned about what makes Caltech special to continue to contribute to the world? In fact, what we do today is going to determine 125 years from now what people will remember about Caltech. So the early years, we started as Throop University in 1891. This is a more familiar picture, of course, of Throop Hall that was on the present-day campus. At that time, there were 6 faculty members and 31 students. We've grown a little since then, but I'll note that our student-faculty ratio is now better than it was then, at 3-to-1 instead of 5-to-1. This is a campus sketch in 1908. You can recognize the central outlines of the campus. This is the well-known architecture of Myron Hunt and Elmer Gray. What is remarkable about this, though, is to remember how different the scientific world was back then. Complete modern conceptions of DNA, of microbes, of an expanding universe, obviously computers, the inner workings of the Earth, were just not known, which is a good reminder of how much we can accomplish in a relatively short time. This was a special time, too. Let me remind you of the Chicago Cubs in the 1908 World Series. Caltech today, of course, we've expanded up to Del Mar here. I love it when alumni come back to campus and they reminisce about the campus stopping right here at San Pasquale. So we have continued to grow a little over this period, but we have not really fundamentally changed in terms of numbers. Our faculty is relatively stable. Our student body is relatively stable because we believe that we can do things in an intimate community that you can't do other ways. And here's an aerial shot, and you'll see taken from roughly the same perspective as that sketch before. It is another special time. For those of you not from Chicago, this is the Chicago wind flag. So it is a nice bookend to the kind of discussion we're having today of triumph in the World Series and also in the intellectual arena. So constancy and change is really the theme of this talk. What are the values that have allowed Caltech to succeed? Above all, concentrated excellence, getting the most creative people from every different background from across the world who have something special to say and something special to contribute. Fearlessness and reinvention. As you know, I've come to this institute from the outside, and it really is an almost overwhelming experience to see how many people on the Caltech campus have seized a big idea and have changed what they're doing because of it. They're just unafraid to change fields, to interact, to think about problems in different ways. Intersection of disciplines. The fact that we're so small, that we haven't grown so much, allows people to come and intersect in ways that you just can't in a much bigger community. Focus. We can't do everything. We have to have the intellectual rigor and discipline to make choices. What is it that's important to do? What is it where we can apply resources, relatively large resources, to make a difference? And that's the whole idea of big ideas, big bets. Discern where you can make that difference, and then put the resources there in a big way. And I will talk in the rest of this presentation now about how we're going to build on some historical strength, areas where we have dominated, and also talk about how can we create new schools of thought. Where are there opportunities that we have not played, but we should? This is not an all-inclusive list, but it is, I hope, a pretty good flavor of the kind of opportunities that we have at this moment to change the world. I like this quote from Nikola Tesla: "The present is theirs, the future for which I really worked is mine." It is a reminder that when we land on Mars, when we discover gravitational waves, when we invent the DNA sequencer, this is what people will remember centuries from now about the progress of humanity. And it is a privilege and also a responsibility to be able to contribute in this fashion. So let me start with neuroscience. From brain circuitry to perception, this is an area where Caltech has had a major role over the years, but I would argue has not really achieved the synergy that's necessary to be a major player, and that's where we have an extraordinary opportunity. This is a picture of Roger Sperry. He did some really important experiments. Actually, they started at the University of Chicago, where he was looking at the wiring of the brain. So he took frogs. If you're a frog, and there's a fly up there, and you see the frog, and he's hungry, the frog's tongue goes back up and gets the fly. The experiment he did was to take out the eye of the frog, sever the nerve, the optic nerve, rotate the eye 180 degrees, and put the eye back in. And the question is, how would the nerves reconnect? Would the brain be plastic, or would the nerves go back to their original wiring? So the question is, which way does the tongue go, given that the eye is rotated 180 degrees? So what happened is the frog is up here, the frog's tongue goes down like this. The nerves reconnected exactly to where they were before. Now, this did not impress his University of Chicago colleagues. In one of the worst tenure decisions ever, he was turned down from tenure, came to Caltech, developed the whole split brain hypothesis, and won the Nobel Prize. So where are we today? We are putting together a new neuroscience institute to bring investigators together across campus to attack this problem. So in the recent NIH Brain Initiative, this has gone on for 2014, 2015, and 2016, the institution with the most awards is Mass General Hospital. They have 12. Second, and the leading institution among all academic institutions, is Caltech with 11. MIT has 10, but let me note in a partisan manner that they're 5 times as big as we are. The important point here is that the reason that we have garnered so many awards is because it's not just biologists. These awards cut across all 6 divisions of Caltech. It's chemists, it's physicists, it's engineers, it's computer scientists, it's social scientists, as well as biologists who are receiving these awards. And that is where our discriminating advantage is, bringing these perspectives together to say something special. And there are huge opportunities here. We have a brain imaging center and a social and decision neuroscience center. We just hired a guy by the name of Dean Mobbs, who looks at people's brains firing under functional MRI. So you put somebody in an MRI, and you bring up virtually a picture of a tarantula. And you see when the tarantula is far away from the toe, that one area of the brain lights up because of anxiety. When it gets really close, a different area lights up because of fear. So one is able to see the wiring of the brain in this fashion. And with Ralph Adolphs and all, the idea here, and this is an image, of how people react, how their brains fire when they're making certain types of decisions, economic decisions, other sorts of decisions. On the more biological side, we have the ability now to go all the way from mapping out single neurons and many neurons firing together to the whole systems approach to the brain-machine interface center. Once we understand how the brain works, how do we use that to develop technologies that can improve the human condition? This is a famous picture from the work of Richard Anderson, where he developed a prosthetic limb for a paraplegic, and the person just thinks, I want to move my arm, and the arm moves because of the wiring, the implant into the brain. The key here is that it was not an intervention in the brain at the motor center. It's not move this muscle, move that muscle, move the other muscle. It was at the point of intent, understanding enough about the brain to understand where you could probe the higher level thought made this all possible. Let's talk about computation. Computation, I believe, is another area where we have not been as competitive as we could, although we have a very interesting history in this way. These, of course, are pictures of Carver Mead and Gordon Moore, who got his PhD here. And Carver talks, at least in the archives, about his first meeting with Gordon Moore. He's a freshly minted assistant professor. He's sitting in his office. In walks Gordon Moore, introduces himself, says, I'm Gordon Moore from Fairchild Semiconductor. Carver says, well, I didn't know who Gordon Moore was, but I certainly knew Fairchild Semiconductor. Pulls out his briefcase. They talk about what engineering's going on. And Gordon, after pulling out a few shirts and socks and stuff, offers him some transistors. Now, this was the time when, individual transistors were a big deal. I remember actually buying my first transistor radio, and on the front, I still have it actually, it says 8 transistors. Now, of course, you have 1 billion transistors on a chip. And some of this work here led, in fact, to the technology that allows you to put 1 billion transistors on a chip. But Gordon was recruiting. He was bringing the transistors to help in terms of the classroom, the education, so our students could really be on the forefront. They get to talking, Carver goes up to Fairchild, consults, and the rest is history, as they say. So this is the start of the information age. And the question is, in terms of computing, where is it that Caltech has a discriminating advantage? Where is it that we can make a special contribution? And I would argue that's at the interface of the disciplines. It's not computer science per se. It's understanding how computer science can really change how we think about a particular problem, how we can get these revolutionary versus evolutionary breakthroughs. The most commonly talked about, of course, is in terms of the genome and trying to understand how you take all this information to be able to develop personalized medicine. But these kinds of general approaches are important for astronomy, they're important for geology. If you could understand how the Earth is shaking at all times, what that means in terms of the structure, not just when an earthquake goes through, but the ambient noise. If you could analyze all that, you would be able to map the structure of the Earth in a different way. It's a huge computational problem, but it would change geophysics if you could do that. So this is obviously a combination both of hardware and of software, and is a huge integration with educational efforts. Our students are voting with their feet. Something like 25% of our undergraduates now are majoring in computer science and information technologies. So there's this wonderful confluence between the research frontier and the educational priorities of our students. Astronomy, discovering new worlds, listening to the universe, is an area where Caltech has led for generations. And is led because basically going back to the day of one of the founders of modern day Caltech, George Ellery Hale, we've appreciated the power of instrumentation. We have helped build and run the major telescopes in the world. So this goes back, this is Mount Wilson, which was the original 100-inch. Here's a picture of Einstein visiting. I love this picture because you have a very nervous Edwin Hubble looking at this theorist trying to operate this telescope. And then, of course, that was followed by the 200-inch Mount Palomar. That is actually being reconfigured right now to look for transients, large-scale events that flash in the sky through combination of modern software, although this is not clearly the largest telescope in the world anymore. But again, with the right ideas and the right program, you can use important instrumentation to make important statements and discoveries. Today, we have even bigger machines where Caltech, again, has made those big bets, has made those big investments so that we can interrogate nature in a different way. And the questions are incredible, from what is 95% of the universe made of to is there life somewhere else in the universe? So we have an opportunity now to look at the universe in very different ways, multispectral, at different frequencies, at different wavelengths. So this, of course, is a picture of at least one of the arms of LIGO, the interferometer that led last year to the discovery of gravitational waves. These are some of the most energetic events in the universe, the coalescing of two black holes. In the few tenths of a second before the black holes come together, there is more energy emitted than all the stars in the universe. Yet you can't see it in light. There's no radio waves, there's no light, there are no X-rays. It's the distortion of space-time. And that was what this wonderfully sensitive machine picked up, giving us an insight into an event in the universe that you can't say anything about in any other way. But there will be other events involving things like neutron stars that will have optical signatures, will have X-ray signatures, and we want to now be able to look at these signatures in gravitational waves, in X-rays, in the light, in infrared, to be able to probe these rare events in detail through different techniques. And we run the largest optical telescope right now, the Keck 10-meter, and we are building, as you know, the 30-meter telescope. So it's the combination, again, of being able to put these together that should lead to a generation of discoveries where Caltech can be an intellectual leader. Related to this, of course, are Planetary Sciences, where the fact that Caltech manages JPL, the Jet Propulsion Laboratory for NASA, gives us an incredible ability to discover transformative notions. This is a picture here of a very young Ed Stone, who is the project leader of Voyager. So here's a mock-up of Voyager. Here is Ed, almost 40 years later, still leading the Voyager mission. Voyager seems to have gotten a little bigger here. It is, of course, much farther away. It has collected bumper stickers at every planet, and it is now out of the heliosphere. And yet, we see the kind of leadership that's necessary, Ed being a former director of JPL and also a longtime faculty member at Caltech. This is a famous image. This was taken on February 14th, 1990. It is the pale blue spot. It is a picture of Earth taken from Voyager 1, 6 billion kilometers away, giving you kind of a sense of the scale we're talking about in this fashion. So where are we now? We're interested, of course, to understand our own solar system. A wonderful story here, of course, is the demotion of Pluto from the planets, and then the same individual, Mike Brown, now working with Konstantin Batygin, has come up with an incredible prediction about a huge new planet 9. We're looking for life on Mars, or evidence of life on Mars, and the ocean worlds like the moons of Jupiter, like Europa, which is covered in ice but has more water under that ice than Earth does. We're also, of course, have identified a huge number of planets orbiting other suns, On average, there is something like 1 planet per star in the universe. So whether we will be able to detect signatures of life is not clear, although I would predict in the next 10 or 20 years we will know in one way or another about at least good possibilities for supporting life that we can see reasonably close by, and this will be a combination of spectroscopy from land-based telescopes and perhaps telescopes flying in space. Of course, you can turn these telescopes not only looking out into the universe, but turn them back and have them face the Earth. And there's a huge amount of data to be taken to map out how the Earth is changing in a time of incredibly rapid change in various parameters of the Earth's climate and environment. We can measure and have missions up there now looking at the salinity of the oceans, sea levels, groundwater, carbon dioxide. And all of these are going to be critical to make sure that human beings can continue to inhabit this planet. Translational sciences is a kind of code word almost, if you will, about what's historically been a tension in university environments about pure research and applied research. In fact, I think that's a false dichotomy. Those boundaries are becoming more and more porous, and people who make basic discoveries often find that it's quite natural to be able to follow them through to their applications. There's huge interest on this campus, and one that we need to support, about being able to use those discoveries, use that knowledge, and turning those discoveries into technologies, into applications, when individuals have that interest. It is not that individuals need to do one or the other. I believe we have to create the environment at Caltech where people can move back and forth easily in this fashion. And this involves interest in diagnosis, therapies, medical devices. In fact, we have the first medical engineering department in the country from engineers, electrical engineers, mechanical engineers, who saw that their skills then could address clinical issues in ways that other people could not. Okay. This is a wonderful picture here of work done by Viviana Gradinaro, among others, developing ways to make the brain transparent, to be able to look inside it, rat brains, not human brains, yet, so that you can actually map out where all the neurons are, and understand by looking inside what you can't when you have an opaque medium. Where we need to situate ourselves, however, is to be distinctive, is to master the basic discoveries, and then to be able to use them as a powerful stimulus for new technologies. That is our competitive advantage, and historically has been. So here are a couple of examples. There's work going on across campus, again, from individuals in all the disciplines. This is the Center for Environmental Microbial Interaction, CEMI. This started out as a method, really a field developed here, geobiology, understanding not only how the Earth became favorable for life, but also then how life changed the geology of the Earth as it developed. But because of the notion of understanding or studying all these microbes, there are incredible potential applications to disease, cancer, autism, cystic fibrosis, how vaccines work, which is all coming out of this. And I love this picture here. This is a picture of Diane Newman and Victoria Orphan, our two new MacArthur Fellows this year. Medical engineering, I mentioned, as an arena where engineers can make devices that can improve human lives. We have activity all the way going from spinal cord implants to sensing blood flow to insulin to developing implants for eyes, which then can unfold in the eye into the proper configurations. So this is an example. Maury Garib has 88 patents in this arena overall, so a serial entrepreneur in that fashion. And entrepreneurship, innovation, turning discovery into impact is something that is part and parcel of Caltech, even though we're not known for it quite as much. So here's a graph. These are patents per 300 faculty members. That, of course, is not an arbitrary number, given that's the number of faculty we have, for Caltech and other leading institutions. And you can see that we produce more than twice as many patents as anyone else per year. We are trying to build now the ecosystem around us. We do not have the same ecosystem as in Palo Alto, the Bay Area, or in Cambridge, or in San Diego. But we're trying to support those faculty who wish to move to the arena of producing commercial products. We have an entrepreneur in residence program. We have a program for our students in business, economics, and management. We have the Caltech Innovation Initiative to provide monies for faculty members to explore transitioning, to get over this so-called valley of death, transitioning from their basic discovery to a potential commercial applications. We're talking about developing an incubator near campus, and we have the Lind Institute to bring together a lot of the curricular innovations and explorations that will support these sorts of endeavors. Geology, geophysics, earthquakes. This is a centerpiece, as you know, for a long time. This is Charles Richter, who developed the Richter scale through fundamental understanding of what's going on in the Earth. Robert Day, who is the descendant of W.M. Keck and Superior Oil, talks about how the advantage he believes of Superior Oil was the connection to geologists at Caltech, so that they understood what was going on in the Earth, and that then translated into a commercial advantage in that fashion. So the basic discoveries lead again to those sorts of changes. We continue to work very hard in this arena. We have been the origin and run an earthquake sensing network up and down the West Coast. We're now trying to develop a more concentrated network, much more granular. This does two things. One is it can give you early alert, seconds to minutes before an earthquake comes. Even seconds can be important, shut off natural gas lines, empty kids out of schools, so on and so forth. And we have 1,000 centers now through our community seismic network through Pasadena, and trying to get into all the schools of the LA Unified School District. That has an educational part of this as well. But it also lets you, if you can imagine having a bunch of tall buildings and putting sensors on all the floors, it lets you understand how the building reacts to the shaking. These are diagrams now of the various modes that propagate up through buildings. And it tells you, in fact, for a particular soil substructure, what is the most robust building in terms of size and construction. And our scientists and engineers look at this, of course, not only in LA, but across the world. A lot of activity in Tibet and also in South America towards this end. This is a great quote from Richard Feynman. And I'm not happy with all the analyses that go with just the classical theory, because nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. This is so Caltech. It's great because it's hard, but it's also fundamental to how the world is constructed. That is, if you're going to build a quantum computer, it is presumably most important when it can tell you something fundamental about nature, because nature is quantum mechanical at its essence. We are investing heavily in this area. We believe there's a new revolution in quantum science that has to do with so-called entanglement rather than discrete energy levels, that will lead to a new generation of devices and will lead to quantum computation, where it's not quite clear yet how quantum computers will affect the world. But one can imagine contributions to, again, simulating, going back to Feynman, some of these really hard quantum questions, understanding what a black hole does, mining large data sets, designing smarter materials because the interactions between the atoms are quantum mechanical, deciphering genetic pathways, and very important in this current day, secure codes that can't be hacked with quantum mechanical mechanisms. Energy and environment is a challenge for all of us across the world, shared by all nations. There's a wonderful Caltech story with Claire Patterson, which illustrates how asking a fundamental question, mastering the basic science, can have really important consequences. So Claire was trying to date the Earth. And he was trying to figure out how old the Earth was by looking at various isotopes of lead, the ratios at different times. And he did that. And he got the right answer, 4.5 billion years, or he got the best answer at that time. But what he also found in looking at lead is he found lead everywhere. He found lead in the air, he found lead in the ground, he found lead in the oceans, where he could date to see where this came from. It was all since the Industrial Revolution. And this, in fact, led to the environmental interventions of removing leaded gasoline and other such productions, which has saved lives, improved quality of lives, and improved the environment. We continue on this pathway. This is the first Caltech electric car from 1968. If you squint a little and imagine, you can see the inner Tesla about to come out. And we continue in this sort of work through the Resnick Sustainability Institute, the Lynn Center for Global Environmental Science. This is the Joint Center for Artificial Photosynthesis, a DOE energy hub, where one tries to harness sunlight to create fuels, to break down water into hydrogen and oxygen. We have a new effort to look at solar power beamed down from space, collect and beam down from space, incredibly ambitious, requires all kinds of work across the disciplines if this is to be successful. And then, of course, JPL is our ace in the hole in this fashion. Let me tell you about the summer experience of one Resnick Institute fellow, Michelle Chareau. So her project was to design lightweight, high-efficiency solar cells. And to do that, you have to combine a number of different approaches. There's basic material science. You have to make ultra-thin molysulfide and tungsten selenide. But because these things are so thin, they don't absorb the sunlight very well. So you have to cleverly understand what's known as nanophotonics. That is, how do you convert the sunlight into the electrons to be able then to collect the energy from the sunlight? And then, of course, you have to make a device. So you have to go to the engineering portion of this to make a full solar cell this way. So a beautiful example of the kind of interdisciplinary collaboration that's necessary to make this work, but the payoff is large. You could get, in principle, if this would work, a raw materials cost saving of a factor of 300, and you could reduce the transportation costs if you're going to shoot these up into space. And of course, the main cost, if you're going to be commercially competitive, is the cost of launch. So it's a question of reducing weight in all kinds of ways. We have to remember that underlying all these possibilities for success, for accomplishment, for contribution, it's the people who do it. We have to remain the destination of choice for incredibly talented individuals. We have to keep the small size and intense focus, which brings people together and lets you make progress. And as you've heard from me many times, I don't believe that there are any shortcuts. You build a great university, one great appointment at a time. And when you go through the faculty process here and the student admissions process, you see the intense work that's involved in evaluating individuals to see how they can contribute, how they can fit. And I want to underscore here that an essential component of achieving excellence is diversity. Unless we are attractive to individuals from every background, every perspective, independent of race, ethnicity, country of origin, sexual orientation, any parameter, unless we are attractive to all these individuals, we will not be the best place in the world because talent is blind. And so we have to be the place that all these individuals want to come. So this is our graduation commencement program from the class of 1915. We've come a little way since then. This is the class of 2015, a little bigger, also a lot more diverse. 44 states, 27 countries represented among nearly 1,000 undergraduates at Caltech. Towards this end, we have a number of goals that we need to meet. We need to bolster our undergraduate scholarships. We are need blind. We welcome individuals. We admit them to the college here independent of their ability to pay. But we need to generate the resources to be able to afford to do that in the best way. And I'd like to get to the point where we eliminate student loans and we are increasing the support we can provide to international students. This is a statement about global diversity in this fashion. As you know, one of the main goals of this campaign, and it will go beyond the campaign, is to be a place which provides graduate fellowships, support for every graduate student. We are of a size with 1,250 graduate students where we could actually do this. So if you are a student coming here, you are not subject to the vicissitudes of federal funding. If you want to work with someone, it doesn't matter if they have a grant or not. You will have your own support. If you want to change fields, there will not be barriers in that fashion. This is good for the students, but in the same way it is good for the faculty, because the better the students, the better the faculty, the better the faculty, the better the graduate students, and one has this wonderful positive feedback loop. Under Gordon and Betty Moore's incredibly generous gift, we have created approximately 200 new fellowships already. And we will continue to move along this way. We have about 500 to create. Finally, let me note faculty leadership chairs. These are not leadership chairs that pay the salary of the faculty member. These are leadership chairs for provost, president, division chairs, institute directors, where the money can be used as seed funds when great ideas come in. The secret to Caltech has been our ability to seize opportunities, to take risks in areas where we're not sure things will work, but if they do, they will transform the world. And this kind of model has worked well, and we need to accelerate. So let me end here with the present is theirs, the future for which we really work is ours. I've changed Tesla's quote a little bit to remind you that it's all of us who need to work together to be able to realize these goals. Thank you.